And look, Radek, someone has pushed the start broadcast button, right?
Who did it?
Definitely avoid our normally nasty talk, right? And dirty talk. So what's up? Right? Can you see me? Can you hear me?
Yeah, I can see just the cameras, but I don't see your presentation.
Okay, my presentation. Okay, let me. Thank you for it. Thank you for this reminder. Yes, now you can see me now.
Yes.
And I mean
Now
it's also me. It's on the screen, which is the go to. Sorry, yeah, it's the presentation for the webinar, and we will start the webinar very soon. As usual, I still see a lot of people are still coming. So let's give it another minute, right? And let's wait. Let's wait for it. Yes, but hopefully everything works, and we are looking forward to the webinar, Radek, right? Because we have been preparing this for really a long time, and in the last minute we can talk about some universal topic to forget the typically dirty language, Radek, right? Which is the weather, right? The weather, typical topic, which used to be a neutral, right? It used to be a neutral topic, right? But in the recent period, weather is also quite questionable, right? Because believe there exists something which what's called the global warming thing, right? Some people don't believe, right? And so we also can talk about it, right? What do you think about global warming, Radek?
I will switch to the flat Earth.
Yeah, right. Flat Earth is my favorite. Yeah. And also flat moon, right? It's
really okay.
Flat moon, yeah, because it's only
side by side. Okay.
Like the interface, right?
Yeah.
Which is always perpendicular to our eyes. Yeah, it's a good one. So shall we
let's move on.
Shall we start? Shall we start?
Let's move on. Yeah.
Let's do that. Let's make it happen. Okay. So what did I want to? Anyway, we will cut it here. So normal people won't
definitely.
see this,
we have
the regular participants can see this already, I think. But anyway, they will forgive us these talks. Okay. So let's start webinar in 10 seconds. Hello, everyone. This is Luboš Pirkl from CFD Support, and I would like to welcome you to the webinar where we would like to show you our fantastic software and workflow and our experience, skills, and our passion and effort we spend on simulations, engineering simulations, and today's topic for the webinar is wind turbine simulations. And as you know, we are quite focused on CFD, FEI, FSI, FEA, FSI, and optimization. And in today's webinar, we would like to show you most of it, how we do it, what we think about it, and what's important when you think about wind turbine simulations. In the beginning, I would mention just quick routines as usual. So webinar is being recorded, and its recording will be later made publicly available. There will be a general part where I will introduce a typical talk about what we are talking about. Then there will be an expert window where Radek, who's our expert, will show you the workflow, how we think it should be done in the engineering simulation software, TCAE. And after that, in the last part, there will be Q&A session, which is dedicated to your questions and our answers. So feel free to ask your questions, and we'll be happy to answer all of your questions. The most important questions, the most representative and relevant questions will be answered right away here in the webinar. And the specific questions will be answered later via email, but you can be sure that all of them will be answered. Let's make a last check if everyone is here. So hello, Radek, can you hear us? Can you even see us?
Yeah, hello, Luboš, and hello to the audience. Yes, I'm here and ready for the webinar, so we
That's
can
great. That's great.
smoothly go on.
Always great to have you here, Radek. You will save this
My
webinar
pleasure.
as usual, and let's do that. So okay, yeah, I'll start with the introduction,
Okay, and
and maybe we can switch
disappear
the
for a
cameras,
while. Yes,
switch the
yes.
cameras off and come back later if we remember it. Yes.
Yeah.
So I'm switching the camera off. Yes. Okay. So still this year there will be last webinar standing in our schedule, which is this blood pump CFD and FEA and FSI and optimization webinar, rounded number 90. So webinar number 90 still this year on December 10. Great to see you there. Yeah, and okay, let's go. So yep, so today's webinar is about wind turbines, and before we go to the topic, I'll mention the couple of necessities, but don't worry, be happy. I'll be quick, and I'll make it as harmless as possible. So CFD Support is the name of our company. We are on the market for 15 years. We are located in Prague, Czech Republic, and we are enthusiastic about CFD, FEA, FSI optimization, and acoustic simulations in all. It's practically all of engineering simulations of all these topics. We I would say our flagship product is software called TCAE. So we develop, maintain, and distribute software called TCAE, which is a comprehensive simulation environment with all of those simulations. And besides that, we do quite a lot of consultancy projects and really the wide range of services around simulations and engineering simulations for the industry. So naturally, I'll be talking a little bit about our software. So the software is called TCAE. It consists of software modules. There are several modules users can play with. I'm sorry, I pushed the wrong button. But I'm coming back. I'm coming. Yes. So the software consists of several software modules. It's extremely flexible because it's been from the beginning created in a way to fit the existing workflows or create new workflows from scratch. So every engineer from the industry can find his or her or their or they workflow. Yeah, sure. And so the workflow can be created. It's extremely flexible, and it can work. Our software works with open source codes, with in-house codes, with other commercial codes, with everything what's available, because it's extremely flexible. From the beginning, we created it in this way. That's one point. It has completely unlimited way of usage, so there are no limitations of number of its users, job scores, hardware installations, so you can be sure that the users or you can use your resources to the fullest. And there is definitely a really wide range of licensing and collaboration options. So in these terms, it's very, very efficient. It's based on open source. This is really a big thing. We are a relatively small company, and we have acquired the ability to make the open source packages work together, to connect together, to create a comprehensive simulation environment. This is really important. So it works on OpenFOAM, ParaView, Calculix, NetGen, OpenVSP, and in fact, there's more than 60 open source projects connected together to create this software. So that's why we are so successful, I would say, because we have merged the open sources. A lot of people spend a lot of enormous time on the open sources. And on top of that, here at CFD Support, we spent more than 50 many years aggregated in a team development of focus development on these simulations. And here I come, what's TCAE best at and for. It's best at turbo machinery simulations and external aerodynamics. These two are really the golden eggs of simulations. It's flexible and it can be used for I would say many other fields, but turbomachinery and external aerodynamics are really the best with TCAE. So TCAE is not software for everything. It's focused, and it can be used as a black box or as a highly sophisticated high-end software where all the options are open. So it's also, I would say, it's also very flexible in terms of way how it is used. It's accurate. It's been proven many times in public benchmarks. Many of them are publicly available. It can be easily automated, and it's in these terms it's ready for usage in the industry. Also, it has a quite wide range of usage in terms of on what resources it's being executed and run. So it can be run on laptops, desktops, clusters, PCs, clouds. It can be used remotely from home or from work. It can be used natively in Windows or natively in Linux. It can be used in graphical interface or in the batch mode. The workflow is extremely consistent and tested for many years. So we believe it's beneficial for the users. There are more than 15 public benchmarks that are very transparent and that can be repeated anytime. We have about 50 tutorials which can be run, which are based on real consultancy projects we did in the past, and we also changed a bit of conditions to not to disclose anything, but the 50 tutorials are based on real consultancy projects, and I believe we have one of the best technical support because we are a small company and we value our users and we go with them the journey, and we never leave them behind, and it's our big proud to share the journey with our clients. Okay, so we have a couple of, I would say, big milestones. No, it's not milestones. It's those are big projects for the future. So we will definitely keep continuing development of the optimization module, which is called the opt. So we will keep pushing the opt. We have the acoustics module, which we believe it's very unique. So the acoustics module will be developed for the future for sure, and we are working on the new module which is called T-Base, and it will allow its users to save the data for the future, save everything in special databases, because we believe that the data is the future, as you know, because of machine learning, etc., etc. And T-Base will allow its users to create their own surrogate models, so to get the simulation results in seconds because of prediction of AI, of trained AI model. So that's what we believe in, and we are moving here very quickly. Recently, we have released the latest release, which is 24.10, and so we have very new version out there, and also we have the light version for those who have limited budget, I would say. Okay, so today's webinar is not exactly about this, but yeah, TCAE has also its light version, which is as cheap as a daily cup of coffee. So anyone who means it seriously with simulations can afford it. Yeah. That's TCAE Lite, and I'll kick off the today's topic. So when we talk about wind turbines, we here mean horizontal axis wind turbines, because those are those really huge machines which are in quite big trend in the recent period, because the energy coming from it harvesting with the wind turbine is renewable. It's considered to be green and very, I would say, popular. And so it's there in trend, and definitely the market is growing, and the need for simulation is growing very quickly, and that's why we are bringing also this webinar, and we are helping several clients already with wind turbines, and that's why today's webinar is here. So we are talking here about specific machines, right? Because they're huge, they are very large. You can imagine that nowadays the largest wind turbines are as large as Eiffel Tower, like really 300 meters high, more than 100 meters long blades. I'm talking here about the offshore wind turbines. And yes, as you can imagine, the power grows with the size of the wind turbine, and also the efficiency grows with the height and with the size of wind turbine. The disc which is covered by the blades is extremely important. The area is extremely important, and it can harvest more and more energy with bigger discs, and also offshore where you can find much better conditions for in terms of energy to get. Okay, so of course our software can simulate these turbines. There are several specifics. As you know, TCAE is great on turbomachinery applications, and this is definitely a mix of turbomachinery and external aerodynamics. So this is where our software meets our users at its best. And there are certain specifics because, for example, these large machines, you cannot always satisfy, for example, the boundary layer and inflation layer and white plus conditions, etc., etc. Also, the size and shape of the domain plays a tremendous role. And in this webinar, we would like to share with you how we think it should be simulated, and it's been tested in the past, of course, many times. So let's go to it. So here it comes. Here he comes, the one who comes after me. I'm not worthy to untie his sandals. And it's Radek. Yes, it's Radek. And let me take a look. Yeah, I'm switching over to him. The presentation has been switched. Yes, it's being switched. Yes, Radek, can you hear us? Perfect. Can you see us? We can see.
I hope you can see me now, and my and
the stage is
my
yours.
Yeah. Thank you, Luboš. So I hope you can see my screen, right? And I will show you an example of simulating wind turbine in our software. So first of all, as usual, I will start on our web pages. So if you go on our web pages and you visit the case study section, you will find the examples to play with TCAE, and one of these examples is our today's topic, which is the wind turbine case. So you can go here, you can download the case, you can see or read some details about the case setup, about the simulation, about the possible outputs, and later on I will show you how this case is set up. So typically, I think it's not a typical CFD project case, because we typically are focusing on a single blade simulation, because to follow all the necessary parameters with respect to the good simulation results, so like the boundary layer, mesh refinement, etc. So we typically focus on a single blade or just a section of the blade to improve it, or to really deeply analyze the properties at certain conditions. So this case is more or less a marketing case, and it shows the general abilities of our software to simulate such a complex applications. So today's will show how to set up this kind of case. So external aerodynamics of the whole wind turbine geometry, both with steady state and transient solver or transient simulation. So let's go for it. So let me go to my computer, and I will run TCAE, so the latest version. which was released almost 1 month ago. So time goes so fast. And I will take directly the case. So let me create, so I will create here. You can create a new case when you're starting from the very beginning. And here I will use this create from other projects. So I will copy the setup of the project, which you can download directly on our web pages. And now I need to find it. So I hope I placed it here, today's date, and yeah, this wind turbine case. So now I am creating new project, and the data, the setup is copied from the existing project because I have run it. Before our webinar started to have simulation data, and now I'm just creating new project with the setup. So as you can see, standard layout, and the geometry looks like this. So we have the external geometry. So we are using here the bounding box, and here we have our lollipop, which looks like a lollipop, which is the wind turbine, covered or suburb by the interface, which defines the rotating region. So here we will have two regions, one rotating, and the rest, the bounding box will build the stationary part, and basically this what we need at the beginning. Just to visualize the input geometry, I can click here on the CFD geometry and decrease the opacity or increase the opacity. And here we have basically the geometry of the blades, of the hub, and of the rest of the wind turbine geometry. So we can see that that the rotating region, the interface, is built in this way. Here in this particle geometry, if I give a proper view, yeah, the other one, so you can see that the turbine is tilted a bit. Yeah, so the turbine, the axis of the turbine is not perpendicular with the, or perpendicular, it doesn't go in the direction of wind direction, so it's a little bit tilted. So we need to count with that when we are setting up the rotation axis. And typically what you have at the beginning, you have just the STL geometry or the geometry of the blades of the turbine, and what you need to create is the interface. So for this kind of propeller simulation, you just need to create a proper cylinder which surrounds the virtual disk of virtual rotating disk of your propeller here, of your wind turbine. So let's start to introducing the case. So first of all, what we need to create is the computational mesh, which is done in the T-mesh module. In the general section, what we define is some general properties. Mainly, the most important one is the scale factor, which says the units of the STLs, because STL geometry itself doesn't hold any information about the units. So you need to know how your STLs were exported. So in this case, the STLs dimensions are in millimeters, so we need to tell it here. And then basically it's all mesh output. If we go for the CFD simulation, we just need a CFD mesh. If we go for finite element analysis, or for both, we need to set the appropriate setup. Let's go for the CFD mesh. So first of all, we need to set the rotating frame. When in case of our application is the turbo machinery, so something is rotating, so we need to have two frames, one static, one rotating, and we need to set the appropriate parameters of the rotation, which consists of the rotation axis direction, and the position on the axis, so point on the axis. So here we need to adjust it in this way to really define in a proper way the rotation of this tilted rotor design. So we have two frames. Typically, the parameters of the axis are the same, because for some scenarios, mainly for the segment geometry, so when we would like to simulate just a segment of the wind turbine, and we both the rotor part and stator part has the segment geometry, so periodic segment, so then we need to have this axis of rotation the same for the static part because the solver or engine inside needs to know the transformation to properly connect the periodicities, etc. So rotation frames, and now we can go for the components where we set the main parameters for the meshing. So what we have here, first of all, for such a kind of simulation, we can enable this at bounding box for external flows option where we define the virtual box, which creates our domain boundaries, flow domain boundaries, and we just say the direction of the flow and the dimensions of our virtual tunnel shape. So we have this. You always need to keep in mind that for external flows, you need to create the domain big enough to get rid of the influence of the boundary conditions. So I think we are now at the edge of the size of the bounding box. So for typically it should be much larger to really be sure that the results will be not influenced by the pressure interaction with the boundaries, etc. So you need to carefully choose the sizing, and here it follows that larger is or bigger is better. So nevertheless, the bigger domain means some troubles for the meshing, because the background mesh should be, or the cells should be large enough to be able to even mesh the domain, and then use the refinement parameters on the important parts, mainly on the rotor and the other geometries, which are analyzed, and refine it to the very high level compared to the big size of the cells far from your object. Okay, so we have component 1, which will create the external part. Here we load it, or we have two options. We can import the geometries, or we can just tell where T-Mesh can find the STL data. So this is the second option. So we use the external data, which are not imported directly into the project. So in this scenario is typically good when you would like to for example, do some optimization steps. So you would like to adjust or improve or modify your geometry designs, which can be regenerated by the external tool, which is placed in the directory. And for the next run, when you reload the case, the new geometry is loaded, and you can run the whole workflow again by one click with a new set of geometries. Here is the table with all the STLs loaded or activated for the geometry. So what we have here, we have the rotor box part. So we have the parts of the rotating interface, which is set as a free interface type, free stream interface type. Then we have the other parts, the housing for the wind turbine compartment, and we have, of course, the tower part, which is fully, because it's static part, and we need to have the domain to be rotational symmetrical, to be symmetrical for the rotation, for a given rotation transformation. So therefore the interface is created in the way that it doesn't cut off the tower in any part. So this is important because when you would like to really do the real rotation, solid body motion, so then you really need to have symmetrical part, and you don't need to include any static part into the domain which are not symmetrical with respect to the rotational transformation. Okay, so the rest part of the geometries is the built-in, which were added by this add bounding box. So we have the inlet, outlet, and the other sides of the bounding box. All right. So here, then we have the minimum and maximum refinement level. So in this case, if I go a little bit lower, here we have the background mesh cell size, which is the largest cell in the domain. And with respect to this sizing, we are setting the refinement. So for example, level 5 means that this cell, which are intersected by the given geometry part, will be refined, which basically means split it up to level 5. So 5 splitting of the hexadras will be done at the given part. So in this way, you refine the mesh with respect to the surface, and to every surface of the wall type of the rigid wall, you can create the gap refinement, or basically it holds for any patch. And this is, I think, done to mesh properly the tiny parts on the interface between the housing of the turbine and other parts, to really be able to mesh these small gaps in the geometry domain. So we don't need to set the high level for all the parts, but we need to just increase the refinement locally for the parts which are too close to get together. Okay, so this is the show background mesh wireframe and the sizing of the background mesh. And here we have the internal point by which you define which part of the domain will be meshed. So I think this is clear. And here we have the refinement region. So typically for external flow application, you would like to refine the mesh more in the neighborhood or in the wake area of your geometry, and keep large cells apart from your geometry, because you need to optimize the cell count with respect to the simulation time. Yeah, so you need to optimize always, because time is so precious, and you need to really go for optimizing the simulation to also from the cost effectiveness point of view. And of course, you can add as many refinement regions as you want. Typically, there is some gradual refinement, so high level of refinement in the neighborhood of your geometry, and for larger wake to resolve the wakes and the flow patterns further from your geometry, which doesn't directly affect so much, for example, the efficiency, the integral values. So you can gradually refine the mesh for different sizing of of these refinement regions. All right, so this was the external part, and here we have the internal part, the internal component. So here we have the STLs for the blade. So each blade has its own STL, and additionally the blade is split into the several parts, like suction parts and pressure parts. So anytime you click here, you will see the parameters or the shape of the given patch. And the blade types, again, you assign the proper types. So typically, I think everything is clear, like wall, or for turbo machine we have a specific names which directly can be connected to the given part of the turbo machinery design. And again, the same as for the component one part. For the static part, we have the interframe, which basically corresponds directly to the outside interfaces from the stationary component. Okay, all the rotating parts. So now because we have in the rotating component, we need to set the reference frame as rotating, and all the walls which are physically rotating, which are basically all walls within the rotational component, needs to be set as a rotating. Again, so here, because we are inside, we are in this rotating region, and yeah, this region is much smaller compared to the bounding box. So we drastically decrease the sizing of the background mesh size, because we need to refine this part much more compared to the general refinement of the stationary part. So we set much lower sizing for these cells, and therefore we don't need to set so much higher refinement level for the blades. So here we have, for example, up to the level 1 or 2, and if we have the different numbers of the refinement for the minimum and maximum level, it means basically that the flat parts are refined with a lower level, and highly curved parts of, for example, pressure side will be meshed by additional level. All right, and yeah, for better mesh alignment, maybe I can show you. So we can also adjust the layout of the background mesh with the tilted rotor. So when I focus, when I change the view, for example, it goes with respect to which is perpendicular to the flow direction, and I will zoom it. So in this way, we will have nicely aligned background mesh with the interfaces, and also with the blades itself, which creates much nicer mesh compared to when we set it standardly with 0 level. So you can see that, yeah, the cells are not so nicely aligned with the interface. So this small adjustment can also improve the meshing. So this is the example of rotate background mesh option. And by this scenario, I think we are fine as the example. Of course, for more detail and more accurate analysis, we can add the boundary layers. The boundary layer is simply added by adding the numbers to the given patch to which the boundary layer should be added. And then if we go for more details about the meshing and the parameters of the mesh, and particularly to the parameters of the layer, we can go to the layer mesh parameters, and we can also play with the local local properties of the boundary layer. So we can set the overall thickness, we can set the expansion ratio, some kind of minimum thickness, but it can stay in these values, and some other parameters which can influence the layer adding algorithm and the procedure. All right, the last parameter is the number of processor which you can use. So on my computer, I am sitting at, I have 10 processors available, so I can save my setup. Not save as, sorry, I would like to just save it. Yeah, basically not save as, because I haven't yet saved it. So I will create wind turbine, for example, webinar. So now so I am lucky that I didn't make any wrong steps. So typically I suggest to periodically save the project to not lose so many steps you have done before your save. And now let me run the meshing. So you can run the meshing whenever your mesh parameters are set. And meanwhile, because it will take some time to mesh the whole region, so it will start step by step. So first it starts meshing the external domain, and then it goes to the internal domain. So meanwhile, I will go further for setting up the CFD simulation. Here, in general, we have the simulation type. So we are going for the wind turbine. So we have a specific type for the wind turbine, because in general, all the turbomachinery applications has, or not all these typical applications, so the different types of turbomachinery applications has different methodology how to evaluate the efficiency, which is the same for wind turbines. So therefore, wind turbine is a standalone simulation type. And for example, if you go to our web pages and you go to our documentation section, which is here, so resources documentation, you will find the TCE manual, and you will find, for example, the efficiency, not for propeller, but for wind turbine. So how the wind turbine efficiency is evaluated. So it has a specific formula which compares the real, so evaluated power of a turbine with respect to the maximum theoretical power of the turbine. So this formula is used, and therefore this type has to be set explicitly to get a proper efficiency, besides other specific or wind turbine specific parameters. Let's go step by step. So in the physics section, we can set the time management, which means that we can tell if we would like to simulate a steady state simulation or transient or both. So here we use the combination of these two. So it works like that. First, the steady state simulation is run, and when this time management is set as steady state plus transient, so then transient is initialized by the result of the steady state simulation. So this helps the convergence for the transient solver, and we typically suggest to start for the turbomachinery application like this, to start with the steady state simulation and then go for transient simulation. As an example, we said that the transient time will correspond to the 4 revolutions of the impeller, of the rotor. In the fluid section, here you choose if your physical model should be incompressible or compressible. Here we can for easy of the simulation and to speed up the simulation, we can go for the simpler model, for the incompressible model, and here you set your parameters of the fluid, of the air typically. In the rotation reference frame, you set the rotating frame, you set the rotational speed. So here we have 15 revolutions per minute. The multiphysics are not applicable for this type of simulations. Here we have the parameters of the turbulence model and the turbulence model itself. So here we choose a k omega SST. If you would like to go for much resolved mesh, so you can go for the hybrid model, for the DS-like model, for better transient and more accurate results. Within the simulation, here we set the parameters of the solver. So we start with the time stepping. So we set the time step as a constant, and the time step again is set proportional to the degrees of revolution of the wheel, so, or of the impeller. And here the time step corresponds to 2 degrees of the revolution of the impeller at a given rotation speed. So it's automatically evaluated this time step. But you can set also for in seconds, or you can set it as adaptive with respect to the current number. Mesh motion is dynamic, so for transient simulation, the rotor will be physically rotating, as we've seen in the animation at the beginning of my part. Here you can go for the numerical order. Typically, when you start with the simulation, you go for the first, and when you are okay, when you are fine with all the setup and the convergence is smooth, then you can go for the second for the higher accuracy. Runtime evaluated quantities. So here are the section where you define what results and what kind of results you would like to see. Averaging window stands for the averaging the solution. both for the transient and the steady state. So averaging window is for the steady state, and transient window is for averaging of transient simulation. Typical transient window is proportional to the revolutions. Typically 1 or 2 revolution is fine to get a nice constant average solution, because typically we would like to have a single value at the end. But as we have seen here, the solution is changing over time. So for example, to evaluate the average power, you need to have nice averaging. So typically averaging of 2 revolution is enough to have a nice constant averaged power value. Maybe we can show it later on in the HTML report. You can ask for example, for fancy visualization like was here, you can ask to evaluate the for example, vorticity or Q criterion. So you can enable it here. Then the efficiency pro, basically you define how, from which patches the torque is evaluated and what are the inlet outlet patches. But here mainly the most important part are the torque patches. You can set additional forces and probe. And when we continue, convergence check. So sometimes it's clever to stop the simulation before the maximum iterations are reached. So you can go for the averaging. You can choose the quantity by which you would like to set your stopping criterion. So for example, here is the power, average power. And if the tolerance, relative tolerance is less than this value, then the simulation can be stopped before the maximum iterations are reached. And finally, boundary conditions. So here we set the speed of the wind. At the outlet, we have standard fixed reference pressure, which is 0, because our reference pressure is set as atmospheric pressure. And for the walls, we are setting standard boundary conditions. So with this resolution, we set standard wall functions and initial conditions, which typically corresponds to the speed of the wind and the pressure, the ambient pressure, or in this case, reference pressure at the outlet. Maybe to conclude this part, this setup part, you can adjust your report, so you can set which parts of the which parts you would like to see in the report, and the units which will be visualized. And at the end of the simulation, you can go, or you can evaluate the HTML report, which can be also found within your project in the TCFD module, which holds the CFD simulation. And here you have the reports both for steady and transient. So I will go for the transient report. And here basically you have a nice overview of your simulations with all the details of the setup of the mesh, how long it took. And here, for example, you can see the efficiency, so final average efficiency point, and you can see here the values throughout your simulation. So this is the blue line is the instant values, and the red one is the averaged. So it's the average over the last 2 revolutions. So you can see that the efficiency is nicely converged and constant. The other quantities you would like to follow, you can follow is the torque. So again, the instant and the averaged one with the final value, and the same holds for the axial radial forces, and finally with the power computed. If the force coefficients are enabled, you can also follow some coefficients and the forces which acting on the given part of the geometry, and the same holds for the torques. Okay, so maybe I see Lubos is back online, so maybe it's time to go back to Lubos to conclude, and then we can show some additional information later during the Q&A or so. So from my side, it's all from this until now, and I think it's time to go back to Lubos.
Indeed, Radek, thank you very much for your part and for your contribution. As usual, it was great and very technically precise, and we've seen what we wanted to see. So thank you for it. Thank you for everything. And okay, I was playing in the meantime with the games with the case what you showed. It's yeah, I definitely like it. It's quite comprehensive. Yeah, there is of course a lot of things we could share about wind turbines. And but time is running. Let's focus on the Q&A session. So I would like to ask the audience to ask your questions. Feel free to ask your questions. We'll be happy to answer them. Yeah. So let me see. At the moment, I can't see many relevant questions, Radek. So, well, I will ask a question if you. Yeah. So Radek, do you believe the global warming exists?
It's not
No.
about if I believe.
Sorry. Yeah. No. It was the question from the beginning. We were just joking a little bit around, and this was just another one, and also this leads me to skip the question about the flat Earth and flat Moon to receive a question. So I'm clicking here. Yes, very well. Thomas is asking, are you able to include blade flexibility based on 6x6 matrices derived from cross-sectional analysis? Oh, well, this is, let me think. Radek, can you blade flexibility during the simulation is really challenging, if this is the question, because simply the mesh, like Radek has shown, is somehow prepared in advance, and then you use it for simulation. The rotation is okay because it's really just the point transformation. That's absolutely okay, but anyway, of blade flexibility, it's could be possible. It's possible as a research project, but not directly, as far as I know. But Radek, what do you think?
Well, our solver doesn't include any flexibility or any mesh adaptation to the any kind of deformation of the blade. So this cannot be done within a single simulation, right? So typically, what we can simulate is the FEA, the static FEA. Then we can include, or we can compute the deformation, and from this deformation we can create new STL, and this STL is put as a new simulation geometry. But this can be done just by iteratively, simulation from simulation, but not within a single simulation. So the forces doesn't flexes the geometry itself during the simulation, but we can do it step by step, right?
Yes.
So if I understand,
it would desire more detailed debate and talks, because we can do quite a lot in terms of like Radek mentioned, the several simulations and several scenarios with geometry changes, but during the simulation, for one simulation point, which is one set of simulation speed and set of boundary conditions, for that it's relatively difficult, and for good reasons, because those are it's possible in theory, but those are extremely challenging and demanding simulations on CPU power and on everything. It's really big simulations. So for that reason, these kind of optimization work can do a better job, we believe, but it as I said, it deserves much detailed discussion, and we are ready to undergo it. So Thomas, feel free to come back with this. Okay, the next question. Saroy is asking, thank you for the webinar. Can this be solved with conjugated heat transfer? I would say yes, conjugated heat transfer is to some level included in the CAE, but again, it would deserve a proper discussion. What and where is shared, and what boundary conditions, and what physics is included, and what not. So
yeah, but in general we can couple it with the FEA part, so we can do a CFD simulation with DCFD, and with the TFEA do the conjugate heat transfer in the solid, and then these two models can be again iteratively connected by updating the temperatures from the results of the FEA, and we can map it back to the CFD to run another iteration, and then again map the resulting temperatures back on the solid part. So some kind of these application we can also handle with the workflow itself, where we include
yes.
both CMesh and TFEA.
Yes. So there are certainly quite a lot of options. It would deserve what's the goal, and what physics is still important and what not, and but yeah, in general it's possible. Yeah. Next question. Thomas has extended his question. He insists that the flexibility is important. Because modern and large turbines can bend by like 10 meters easily, and they can twist, and they can really they can really deform, which is absolutely correct. We know it, and again, still the same answer. During the simulation, we think it's inefficient to change the topology. Maybe we will change this strategy in the future. But it seems that with our current knowledge, during the simulation, changing the blade structure or topology or bending, basically bending, let's call it bending for wind turbines. It's clear what it means. Bending the blades during the simulation is somehow inefficient. But let's talk about it. We can get back to it in separate discussion via email. Yeah. Thomas, right? Thank you. So I think he understands it. But let's think about it. There are tools. We only think they're inefficient. That's all. Yeah. The Saroy is writing making more precise question. The goal is to obtain metal temperature distribution to creep and fatigue analysis. Yes, for this, its software is ready. So we can there's FSI, which is one-way FSI, which works well for turbo machinery applications. Somehow it's here similar to the Thomas question, which means as long as the deformation is not that large and the flow stays very similar, then one way FSI is good enough, and for that we can transform the forces and temperature, for example, to the solid, and the solid solver, the Calculix, can do this loaded blades simulation, which arises in deformation and material stresses. So that's certainly possible. The fatigue is a question. It depends how the data would be used further. Our software don't do fatigue analysis, only material stresses, deformation, and modal analysis of rotating objects. Yeah. So yeah. So it seems that we don't have any relevant questions. Those questions which are specific, we will gladly answer later via email. That's for sure. But for the whole audience, I think we're done here. So I will conclude.
Yeah.
Sorry. Yeah, I'm still presenting. I forgot already. So well. So Q&A is over, and it's time to conclude. Radek, anything on your mind?
Yeah, thank you very much. We nicely fit in 1 hour span, so we can conclude by thank you for watching, and we'll gladly wait for your additional questions to discuss via email or via any other channel. And yeah, have a nice day and see you next time.
Okay, thank you everyone. Thank you for your time. Let us know how we can help, and we leave you with that. And thank you for now. Bye bye.
Bye bye.
Bye bye.